Welcome! In this session, we'll explore an exciting problem titled Maximum Number of Points with Cost. Together, we'll dive into the details of this problem, understand the constraints, and evaluate different approaches to solve it effectively. Let's get started. This problem revolves around a matrix called points, where each cell contains a specific number of points. The objective is to find the maximum number of points you can collect by traversing the matrix row by row. You can start from any cell in the first row and move to any cell in the subsequent rows. However, there's a catch: moving between columns comes with a cost, which is the absolute difference between the column indices of your current and next cell. Your task is to maximize the total points collected while accounting for these movement costs. The output should be the maximum points you can achieve after traversing from the first row to the last row. Let's take a look at the first example. The input matrix is 1, 2, 3, 1, 5, 1, 3, 1, 1. Here, the output is 9. To achieve this, start from the cell points 0, 2, equals 3 in the first row, which is the third column. From there, move to points 1, 1, equals 5 in the second row, which is the second column. The cost of this move is abs, 2 to 1, equals 1. Then, move to points 2, 0, equals 3 in the third row, which is the first column. The cost of this move is abs, 1 to 0, equals 1. This path gives you the highest total points after subtracting the movement costs. When summing everything up for this example, the total points collected are 3 plus 5 plus 3, and the total movement cost is 1 plus 1. Subtracting the costs from the collected points gives a result of 9. Now, let's consider another example. Here, the input matrix is 1, 5, 2, 3, 4, 2. The output for this case is 11. To achieve this, start at points 0, 1 equals 5 in the first row, which is the second column. Then, move to points 1, 1 equals 3 in the second row, staying in the same column. The cost of this move is abs, 1 to 1 equals 0. Finally, in the second example, you move to points 2, 0 equals 4 in the third row, which is the first column. The cost of this move is abs, 1 to 0 equals 1. Summing up the points, you get 5 plus 3 plus 4, and subtracting the movement cost of 1, the total points collected are 11. Now, for a third example, consider the matrix 10. Here, there is only one row and one column. With no movement required, the maximum points collected are simply the value of the single cell, which is 10. This problem also comes with certain constraints. The matrix can have up to 10-5 rows, and each row can have up to 100 columns. Each cell in the matrix contains a positive integer between 1 and 10-5. Additionally, there are specific edge cases to consider. If the matrix has only one row and column, the result is the value of that single cell. If there's only one row but multiple columns, the result is the maximum value in that row since no movement costs apply. For large matrices, the solution must be optimized to handle the upper limits efficiently. Finally, if all cells have the same value, the result will depend entirely on minimizing movement costs. To tackle this problem, we considered two main approaches. First, the brute force approach. The intuition here is straightforward. We aim to maximize points by exploring all possible transitions from each cell in one row to every cell in the next row. For every pair of cells, we calculate the transition cost, which depends on the absolute distance between their column indices, and dynamically update the maximum points. While this method is simple and intuitive, it has a significant drawback. It involves a nested computation for every pair of cells, leading to a time complexity of m*n squared, where m is the number of rows and n is the number of columns. This becomes computationally prohibitive for larger matrices, such as when n is in the range of tens of thousands. Instead, we turn to an optimized dynamic programming approach. This method focuses on reducing redundant computations by leveraging the structure of the problem. Specifically, we observe that the movement cost between columns can be pre-computed efficiently using two linear sweeps, one from left to right and another from right to left. These sweeps allow us to minimize the cost dynamically while calculating the maximum achievable points row by row. By adopting this optimized dynamic programming approach, we achieve a significant improvement in efficiency. The time complexity is reduced to m*n, because we only need to perform linear sweeps over each row instead of nested iterations for every pair of columns. In terms of space complexity, we require just O, n, as we only store the DP array for the previous row at any given time. This approach not only scales well for large input sizes but also ensures correctness. We chose this strategy because it strikes the right balance between efficiency and implementation complexity. Compared to the brute force method, which is simpler conceptually but computationally expensive, the optimized DP approach is more sophisticated but achieves substantial performance gains. The trade-off here is clear. While the optimized solution requires a bit more effort to implement, the reduction in time complexity from O, m*n squared to O, m*n makes it far more practical for large matrices, especially in competitive programming contexts. The key insight driving this solution is that the primary bottleneck in naive approaches lies in handling column transition costs. By pre-computing maximum values through efficient left-to-right and right-to-left sweeps, we eliminate redundant calculations and streamline the process. The problem's natural structure, where transitions occur row by row, aligns perfectly with dynamic programming, allowing us to break it into smaller, manageable subproblems. With this optimized approach, the overall time complexity is O, m*n, and the space complexity is O, n, making it capable of handling large input sizes effectively. This strategy not only ensures scalability but also represents the most practical and efficient solution to this problem, making it well-suited for real-world scenarios where performance is critical. In this problem, we aim to maximize the points collected while transitioning row by row within a matrix. Each cell in the matrix contains a certain number of points, and the cost of transitioning between two cells depends on the difference in their column indices. Specifically, the cost is the absolute difference between the column indices of the two cells. The challenge is to compute the maximum achievable score efficiently. One way to approach this is by using a brute force method. Here's how it works. First, we initialize the necessary variables, including the matrix representing the points grid and a variable called max_points to keep track of the maximum score obtained. Then, we iterate through the rows of the matrix. For each cell in the current row, we explore all possible transitions to every cell in the next row. By iterating through all combinations of transitions, we can calculate the total points for each path, which is the sum of the points in the current cell and the next cell, minus the transition cost. This approach ensures that we evaluate all possible paths to find the optimal one, but it's computationally expensive due to its nested loop structure. The total points for any transition are determined by considering three components: the points in the current cell, the points in the next cell, and the cost of transitioning between the two cells. The transition cost is calculated as the absolute difference between the column indices of the two cells. For each possible transition, we compare the calculated total points with the current maximum points stored in max_points. If the new value is higher, we update max_points accordingly. This process is repeated for all rows in the matrix, propagating the maximum points from one row to the next. Once we've processed all rows, the max_points variable will hold the maximum achievable score. While brute force guarantees the optimal solution by exploring every possible path, it comes at a significant computational cost. With a time complexity of O, m*n squared, where m is the number of rows and n is the number of columns, this approach becomes impractical for large matrices. However, it provides a thorough foundation to understand the problem and serves as a baseline for optimization. The brute force approach highlights why the transition cost is such a critical part of this problem. The cost penalizes transitions to distant columns, meaning that jumping across large parts of the matrix is expensive and requires careful consideration. This makes the problem more complex than simply summing the maximum points in each row, as greedy methods that don't account for the cost will fail. For edge cases, the behavior of the algorithm is straightforward. If there's only one row in the matrix, there are no transitions to consider, and the result is simply the sum of all cell values in that row. In the case of a single column, transitions are trivial since there's only one possible path through the matrix. However, for large matrices with many rows and columns, the brute force approach quickly becomes infeasible due to its quadratic dependence on the number of columns. This is why it's crucial to explore more efficient solutions. To implement the brute force method, we rely on a few basic data structures: the matrix itself, which allows constant time access to any cell's point value, and the max_points variable, which is updated in constant time during each comparison. To address the inefficiency of the brute force approach, we can leverage key optimizations. One such optimization is to reduce redundant calculations. Instead of recalculating the transition cost for every pair of cells, we can pre-compute reusable values or adopt a dynamic programming strategy. In this optimized approach, we maintain a DP array where each element represents the maximum points achievable at a specific column in the current row. To transition to the next row, we update a new DP_next array by considering the maximum achievable points from the previous row for all column transitions. This reduces the time complexity to O(m*n), as we no longer have nested loops iterating over all pairs of columns. For even greater efficiency, we can apply a sliding window technique to minimize calculations during the transition step. By carefully managing the maximum values within a sliding range, we can reduce the computational complexity of the transition step to O(n) per row. These optimizations drastically improve performance, making the algorithm scalable even for large matrices, while still guaranteeing the optimal solution. Here, we begin by defining a class solution with a method maxPoints that takes the points matrix as its input. First, we determine the number of rows and columns in the matrix. Then, we initialize a dynamic programming array DP with the values of the first row, because the first row's points are our starting point. This DP array will help us keep track of the maximum points attainable at each column as we process subsequent rows. Next, we iterate through each row, starting from the second one. For each row, we create two helper arrays, left and right, which will store the maximum values achievable when traversing from left to right and right to left, respectively. These arrays are essential to efficiently calculate the maximum points for the current row by considering the constraints on movement costs. The left array is computed first. We initialize the first element of left to the first value of DP, and then for each subsequent column, we calculate the maximum value between the previous column and left -1 and the corresponding value in DP. This accounts for the movement cost as we traverse from left to right. Similarly, the right array is computed by starting from the last column and moving right to left, where we consider the maximum between the next column and right -1 and the current DP value. These two arrays allow us to efficiently determine the best possible values for each column in the current row. Finally, for every column in the current row, we update the DP array. Each element in DP is set to the sum of the current cell's points and the maximum value between the corresponding entries in the left and right arrays. This ensures that the DP array now represents the maximum points attainable at each column after processing the current row. Once all rows have been processed, the answer to the problem is simply the maximum value in the DP array, which we return at the end. This value represents the highest number of points achievable across all rows and columns, adhering to the movement cost constraints. To solve the problem of finding the maximum number of points with cost, we start by importing the necessary utilities and defining our solution class. The main method here is maxPoints, which takes a two-dimensional array, points, representing the grid. First, we determine the number of rows and columns in the grid. Next, we initialize a DP array to store the maximum points for each column in the first row. This is done by simply copying the values from the first row of the grid into the DP array. Once the first row is set, we iterate through each subsequent row, beginning from the second. For each row, we create two helper arrays, left and right, to track the maximum values when traversing the DP array in two directions. We start by computing the left array, where each element stores the maximum value encountered while moving from left to right, adjusted by subtracting 1 at each step to account for the cost of jumping between columns. After computing the left array, we move on to calculate the right array, which tracks the maximum values when traversing the DP array from right to left. Here, we adjust the values similarly by subtracting 1 at each step. With both the left and right arrays computed, we can update the DP array for the current row. For each column, we calculate the new DP value by adding the points at the current cell and the maximum of the corresponding values in the left and right arrays. This ensures that we account for the optimal path to the current column. Once all rows are processed, the maximum value in the DP array represents the highest number of points achievable. We iterate through the final DP array to find and return this maximum value, completing the implementation of the solution. We begin with a small grid example. The input grid has 3 rows and 3 columns, and we start by initializing dp with the first row values, which are 1, 2, 3. Now, as we process the second row, we first compute the left array. This array helps us track the maximum scores achievable when moving from the left side of the grid. The first value in left is simply the first value of dp, which is 1. For the next column, we calculate left, 1, as the maximum of left, 0, 1 and dp, 1, resulting in 2. Finally, for left, 2, we take the maximum of left, 1, 1 and dp, 2, giving us 3. This completes our left array for the second row as 1, 2, 3. After computing the left array, we move to the right array, which tracks maximum scores moving from the right side of the grid. For right, 2, we start with the last value of dp, which is 3. Next, right, 1, is calculated as the maximum of right, 2, 1 and dp, 1, yielding 2. Finally, right, 0, becomes the maximum of right, 1, 1 and dp, 0, resulting in 1. This gives us the right array as 1, 2, 3. Using the left and right arrays, we compute the new dp for the second row. For each column, we add the grid value at that position to the maximum of the corresponding left and right values. This results in a new dp of 2, 7, 4. Next, we move to the last row, where the process begins similarly by calculating the left array. Starting with left, 0 equals dp, 0 equals 2, we calculate left, 1, as the maximum of left, 0, 1 and dp, 1, which gives 7. Finally, left, 2, becomes 6, making left equals 2, 7, 6. Now, we compute the right array for the last row. Starting with right, 2 equals dp, 2 equals 4, we calculate right, 1, as the maximum of right, 2, 1 and dp, 1, which results in 7. Finally, right, 0, becomes the maximum of right, 1, 1 and dp, 0, giving us 6. This results in right equals 6, 7, 4. Using the left and right arrays, we now compute the new dp values for the last row. For the first column, we take the grid value 3 and add the maximum of left, 0, and right, 0, resulting in 9. For the second column, we take 1 and add the maximum of left, 1, and right, 1, yielding 8. Lastly, for the third column, we add 1 to the maximum of left, 2, and right, 2, which is 7. This gives us the final dp of 9, 8, 7. The maximum value in dp is 9, which is our result for this grid. In the single column example, the grid has 3 rows and 1 column. Here, we initialize dp with the first row value, which is 4. Since there's only 1 column, both the left and right arrays are identical to dp, starting with 4. For the second row, we calculate the new dp by adding the grid value 2 to the maximum of the left and right values, resulting in 6. This updates dp to 6. Moving to the third row, the left and right arrays remain 6, since there is still only 1 column. Adding the grid value 6 to the maximum of left, 0, and right, 0, gives a new dp value of 12. Thus, the final dp for this grid is 12. The output for the single column grid is straightforward. The maximum value in the final dp array is 12, which is our result. Now, let's consider a larger grid with uniform values. Here, the input grid has 3 rows and 3 columns, with all values being 1. We start by initializing dp with the first row values, which are 1, 1, 1. For the second row, we calculate the left and right arrays. Since all values in dp are the same, both left and right arrays remain 1, 1, 1. Adding the grid values to the maximum of the corresponding left and right values gives us a new dp of 2, 2, 2. For the last row in the uniform grid, the left and right arrays are again 2, 2, 2 because all values are equal. Adding the grid values to the maximum of left and right results in a new dp of 3, 3, 3. The maximum value in this final dp array is 3, which is the result for this grid. This example demonstrates that when all values in the grid are uniform, the maximum achievable score simply increases by the row number as you progress through the grid. To analyze the time complexity of the solution, we start by noting that the dynamic programming approach involves several key steps. First, we initialize the dp array with the values of the first row, which takes calls time.
Then, for each subsequent row, we iterate over all columns.
Within this iteration, we calculate the left array by updating a running maximum as we move from left to right, and this computation takes calls time for each row. Similarly, computing the right array as we move from right to left also requires calls time per row. After calculating these arrays, we update the DP array by iterating over each column and combining the values from left and right, which again takes calls time per row. Finally, at the end of all the rows, we find the maximum value in the DP array, which takes an additional calls time. When we combine all these operations, the dominant term is rows asterisk calls, as these are the operations that scale with both dimensions of the input matrix. Therefore, the total time complexity is rows asterisk calls.
Now let's focus on the space complexity.
The space usage is determined by the auxiliary data structures used during computation. The DP array, which stores intermediate results for the current row, has a size of calls. Additionally, for each row, we compute the left and right arrays to track running maximums, and these arrays also have a size of calls each. Importantly, all three arrays DP, left, and right are reused for every row, so their total contribution remains calls. The input matrix itself does not contribute to auxiliary space since it is part of the problem's input. As there are no additional data structures outside of these arrays, the overall space complexity of the solution is calls.
Now let's compare this optimized solution to a brute force approach. In a naive solution, we would iterate over all possible combinations of column choices for each row.
This would require evaluating every possible column pairing for all rows, which results in an exponential time complexity of calls rows. Additionally, a recursive brute force solution would require rows space for the recursion stack. However, the given dynamic programming solution significantly improves upon this by reducing the time complexity to rows asterisk calls. This is achieved by leveraging the left and right arrays to maintain running maximums, allowing us to avoid redundant computations. Regardless of input size or values, the algorithm still processes each row and column exactly once, so the best and worst case time complexity remains rows asterisk calls.
Finally, let's justify the time and space complexities mathematically.
The outer loop of the algorithm iterates over all rows in the matrix, and for each row, the operations performed scale linearly with the number of columns. This results in a time complexity of rows asterisk calls, as the algorithm must process every row and column. As for the space complexity, the DP, left, and right arrays are the dominant contributors. Each of these arrays has a size proportional to the number of columns, and they are reused across all rows, so the auxiliary space used is calls. This confirms that the overall time complexity is rows asterisk calls, and the space complexity is calls.
When solving this problem, there are several common mistakes that candidates often make.
First, ignoring edge cases can lead to failures in critical scenarios, such as handling an empty input, a matrix with just one row, or extreme values that might cause index errors. After implementing your solution, always explicitly test these edge cases.
Another frequent issue is overlooking optimization opportunities. While starting with a brute force solution is fine, it's important to transition to more efficient approaches like dynamic programming.
You should analyze your time complexity and aim to reduce redundant calculations wherever possible.
A third mistake involves incorrect transition logic in dynamic programming. This often stems from failing to properly define how the state transitions between rows or overlooking transition costs. Deriving the recurrence relation is key here, so take time to carefully validate it.
Additionally, misunderstanding the problem constraints can be a major pitfall. For example, if the problem specifies a matrix with up to 10,000 rows, your solution needs to scale efficiently. Finally, watch out for indexing errors, as problems may describe the matrix using 1-based indices, while your implementation typically uses 0-based indexing. Mixing these up can result in frustrating bugs, so stay consistent throughout your code. Now, let's focus on insights that can help you succeed in interviews.
Recognizing patterns is a crucial skill. Many matrix traversal problems reduce to finding optimal paths under specific constraints. Knowing whether the problem requires greedy methods, dynamic programming, or even graph-based approaches can save you significant time during the interview. Another tip is to consider space optimization in dynamic programming.
If your solution only needs the previous row's data, reduce your space complexity to O(n) by storing just the last row instead of an entire DP table. Interviewers also value your ability to communicate trade-offs. For example, if you optimize your solution from O(n) superscript 2 to O(n asterisk log n), be prepared to explain why the transition was necessary.
Lastly, deriving recurrence relations is often the most challenging part of dynamic programming problems.
Interviewers want to see your thought process here, so take time to articulate how you arrived at the recurrence and why it works for the problem constraints. There are several related problems that you can practice to deepen your understanding of this topic. For example, LeetCode 931, 1289, 64, and 174 all involve variations of matrix path optimization. These problems share similar concepts, such as minimizing or optimizing costs as you traverse the matrix. Additionally, let's look at alternative approaches you can use to solve this problem. Brute force is the most straightforward method, where you try all possible paths row by row. While it's simple to implement and easy to understand, it comes with a significant trade-off. Its time complexity is O(m*n superscript 2, making it impractical for large inputs.
A more efficient option is dynamic programming with a row-based approach.
Here, you calculate the minimum cost to reach each cell in the current row based on the values in the previous row. This approach has a time complexity of O(m*n), making it a balanced choice. However, it may require O(m*n) space unless you apply further optimizations.
For even better efficiency, you can use space-optimized dynamic programming.
Instead of maintaining the entire DP table, you only store the current and previous rows, reducing the space complexity to O(n).
This saves memory and is particularly useful for large inputs, though it may involve slightly more complex code. Another advanced technique is monotonic queues or sliding window optimization.
These are especially useful for scenarios involving a limited transition range between rows. By applying sliding window techniques, you can reduce the time complexity to O(m*k), where k represents the transition range. While this method is highly efficient, its implementation is more complex and requires a solid understanding of the underlying algorithm.
Choosing this approach depends on whether the problem constraints justify the added complexity.
Balancing efficiency with clarity is key, so always weigh the trade-offs based on the problem requirements and your familiarity with these techniques.
Thank you for staying with us through this problem.
We summarized the key concepts, discussed approaches, and highlighted important takeaways. Keep practicing, and don't forget to explore variations of this problem to strengthen your problem-solving skills.
See you in the next session. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!